The light touching your skin right now is 1 million years old. Not 8 minutes old, though that is the figure you may have heard, and it is true as far as it goes. The journey from the surface of the sun to the surface of your skin takes about 8 minutes and 20 seconds. Light travels at roughly 300,000 kilometers per second, and the sun is approximately 150 million kilometers away, so the arithmetic is quick and the number is well known. But that 8-minute figure describes only the final leg of the journey. The actual age of the photon striking you now, the age of the light itself, measured from the moment its energy was first created, is something else entirely.
Every photon the sun emits begins its life in the core. The sun's core is a volume about 20% of the total solar radius, a sphere roughly the diameter of Jupiter, and within it, the temperature reaches 15 million degrees Celsius. At that temperature, hydrogen nuclei, bare protons, stripped of their electrons, move fast enough to overcome their mutual electromagnetic repulsion and collide with sufficient force to fuse. This is nuclear fusion, the binding of lighter nuclei into heavier ones, releasing energy in the process. In the sun's core, 4 hydrogen nuclei fuse through a sequence of reactions to produce one helium-4 nucleus, releasing photons and neutrinos, and a quantity of energy given by Einstein's equation relating mass to the speed of light. Every second, the sun converts approximately 620 million metric tons of hydrogen into helium. The helium nucleus that results is slightly less massive than the 4 hydrogen nuclei that combined to make it. That missing mass, roughly 0.7% of the original, becomes energy. The energy produced at the core is staggering by any terrestrial standard, but the core is also extraordinarily dense. The plasma there has a density roughly 150 times that of water. A photon born at the center of the sun does not travel outward in a straight line. It travels in a random walk, absorbed almost immediately by a nearby particle, re-emitted in a random direction, absorbed again, re-emitted again.
Progress outward, net of all these redirections, is negligibly slow. A photon crossing the solar interior this way takes, on average, somewhere between 100,000 and 1 million years to reach the surface. 1 million years. Sit with that number for a moment. The photon now crossing the 8-minute void between the sun and your eyes was created in the solar core before modern humans existed. Before our species walked out of Africa. Before Neanderthals painted their caves. Before the last common ancestor of humans and chimpanzees drew its first breath. The energy you are receiving now was already making its slow, interrupted way toward the edge of a star. It has been traveling since before anyone was here to wonder where it came from.
And now, after all of that, it arrives. It touches you. And you probably did not think about it at all. The sun has been doing this for 4.6 billion years. That number, 4.6 billion, is almost completely resistant to human intuition. We can say it, we can write it, we cannot feel it. Our nervous systems evolved to track threats and opportunities across timescales measured in seconds, minutes, days. We can extend our imagination to years with effort, to decades with concentration, to a century with genuine strain. Beyond that, the number becomes a label rather than a felt quantity. 4.6 billion years is not a long time in any sense we can genuinely access.
It is simply a very large number attached to the word years. But the sun does not care what timescales we find comprehensible. It has been fusing hydrogen at its core continuously, without pause, for longer than Earth's rocks have existed, longer than the oldest fossils, longer than the oldest mountains, which are themselves incomprehensibly old by human standards. The sun has been burning since before the solar system was a solar system, since before any of the planets existed, since before the disk of gas and dust that would become everything we know had coalesced into discrete objects with distinct orbits.
The sun was already there, already fusing, already pouring light into the surrounding void, when the first grains of dust that would eventually become your planet first stuck together. It formed from a cloud of gas and dust, a nebula of hydrogen and helium left over from the formation of the Milky Way, seeded with heavier elements forged in the cores of earlier stars that had already lived and died. Gravity drew that cloud inward. The center compressed and heated until the temperature crossed the threshold for nuclear fusion and a star ignited. That moment of ignition.
The planet you are lying on formed from the leftover material in the disk surrounding the young sun, assembled by impacts over tens of millions of years, reaching its present form roughly 4.5 billion years ago. In the classification system astronomers use for stars, our sun is a G-type main sequence star, a category sometimes called a yellow dwarf, though its light is closer to white than yellow, and its mass places it slightly above the average for stars in this galaxy. It is a middle-aged star, not remarkable, not exceptional. One of roughly 200 billion stars in the Milky Way, the vast majority of which are smaller, cooler, and redder than the sun. It is not the largest star in its galaxy.
It is not the brightest. It is in most respects completely ordinary. This ordinariness is worth sitting with. We orbit an average star. We depend on it for everything, for the warmth that keeps liquid water stable, for the energy that drives photosynthesis and the carbon cycle and the food webs that make complex life possible, for the light by which we see the world. Every civilization that has ever existed has oriented itself around the sun. Calendars, agriculture, architecture, religion, all of it organized around the rhythm of a star, so ordinary that, viewed from several light years away, it would be invisible to the naked eye. And this star is slowly, quietly, permanently changing. The sun is not in a steady state.
It has been burning through its hydrogen reserves for 4.6 billion years, and the process of burning is not static. As hydrogen in the core is converted to helium, the composition of the core changes. The mean molecular weight of the core material increases. To maintain the pressure required to balance the inward pull of gravity, the core must compensate. It runs slightly hotter, burns slightly faster. The result is that the sun has been growing gradually brighter throughout its history. When the sun first ignited 4.6 billion years ago, it was approximately 70% as luminous as it is today.
If you could go back to early Earth, when the first microbial life appeared in the oceans, the sun above would have been visibly dimmer. Not enough to notice in a casual glance, but enough to make the energy budget of the young planet significantly different from what it is now. Earth has always been adapting, continuously and invisibly, to a star that keeps turning up the dial. The dial is still turning. It will not stop. This is not a catastrophe waiting to happen in some distant and ignorable future. It is a process already underway, governed by physics that does not negotiate, moving at a pace that makes human history look like a single heartbeat in a million-year sleep.
The sun we take for granted is not the sun that always was. It is not the sun that will always be. It is the sun of this particular moment, 4.6 billion years into a 10 billion year life, and it is already past the halfway point. What that means for the world below it is a question whose answer unfolds slowly over spans of time that language struggles to contain. This is where the story begins, not with a catastrophe, not with a collision or an explosion or a sudden failure, with a star, middle-aged and ordinary, that has been changing since before anyone existed to watch it change, and that is still changing now.
The word catastrophe implies suddenness. We tend to imagine planetary disaster as an event, an asteroid strike, a supervolcano, a gamma-ray burst reaching across the galaxy to sterilize a world in seconds. These are real possibilities. They have happened in Earth's past and will happen again. But there is another kind of catastrophe, one that operates on a timescale so vast it is almost impossible to feel as danger. It does not arrive, it accumulates. It is the kind of catastrophe that does not announce itself and has no single moment you could point to and say, that is when things went wrong. The sun's brightening is that kind of catastrophe.
According to the standard solar model, the astrophysical framework first developed in the mid-20th century and refined continuously through the following decades. The sun's luminosity increases by roughly 10% every billion years. This figure comes from the same physics that governs the core's hydrogen consumption. As helium accumulates in the core and the mean molecular weight rises, the core temperature must increase to maintain pressure equilibrium, and the higher temperature drives more fusion, producing more energy. 10% per billion years. The number is not dramatic. It does not sound like a warning. But applied across geological time, it describes a world becoming steadily less habitable. 1 billion years from now, the sun will be approximately 10% brighter than it is today.
10% more luminosity reaching Earth means significantly more energy in the atmosphere and at the surface. Climate systems are not linear. A small increase in solar input feeds back through the water cycle, through atmospheric chemistry, through ice and albedo and vegetation cover, in ways that amplify the initial perturbation. Climate models suggest that even without human emissions, a sun 10% brighter than today's would push Earth's average surface temperature past the point where oceans remain stable. The oceans would not boil immediately. The process is more gradual than that, but the feedback dynamics would begin a cascade that ends with liquid water disappearing from the surface entirely. The mechanism is called the moist greenhouse effect. As surface temperatures rise, more water evaporates into the atmosphere.
Water vapor is itself a greenhouse gas. It traps infrared radiation and warms the planet further. More warming drives more evaporation. More evaporation increases the concentration of water vapor. The feedback loop accelerates. At some threshold, the process becomes self-sustaining, a runaway that no natural mechanism can reverse. The upper atmosphere becomes saturated with water vapor.
Ultraviolet radiation from the sun begins to break water molecules apart in the upper atmosphere, a process called photodissociation. The liberated hydrogen, light enough to escape Earth's gravity, drifts upward and
It is roughly equal to the span of time between the formation of Earth and the appearance of the first simple cells. It is twice the age of the oldest complex multicellular animals. It is 1,000 times the duration of the entire Phanerozoic eon, the 500 million years that contains every animal, every plant, every ecosystem that has ever left a fossil record. 1 billion years is, by any intuitive measure, essentially forever. And yet the physics does not care about our intuition. The physics runs on the same clock, regardless of whether we find the timescale comprehensible or not. 1 billion years from now, barring some intervention that cannot currently be imagined, Earth's surface will be sterile.
The process that ends complex life on this planet has already begun. It is simply moving too slowly for any living generation to perceive it as movement. There is something philosophically important about this. We tend to evaluate threats by their immediacy. An earthquake that kills thousands next year registers as real. A process that will kill everything in 1 billion years registers as abstract. But the process is no less certain for being slow. The timetable is precise. The physics is unambiguous. The only thing separating the moist greenhouse catastrophe from any other extinction-level event is time. And time, in this context, is not a reprieve. It is the mechanism of delivery.
Consider what you are actually describing when you say the sun will grow 10% brighter over the next 1 billion years. You are describing a star that will, by increments too small to measure in a human lifetime, too small to measure in the entire span of recorded history, too small to detect without instruments of extraordinary precision, move the boundary of the habitable zone outward, a zone, the range of distances from a star where liquid water can exist on a planetary surface, that currently includes Earth will, in geological time, migrate outward until Earth sits inside the inner edge, where Venus already sits. The habitable zone will not find a new home at Earth's location.
Earth will find itself outside the habitable zone, on the wrong side of a boundary that moved without making any sound. Venus is a reminder that this outcome is not hypothetical. Venus orbits closer to the Sun than Earth does, and current models suggest it may once have had liquid water, possibly even a shallow ocean, in the early solar system when the Sun was dimmer. As the Sun brightened over the first 2 billion years, Venus crossed the threshold. The moist greenhouse took hold. The oceans evaporated. The hydrogen escaped. What remains is an atmosphere of carbon dioxide and sulfuric acid, a surface pressure 90 times that of Earth's sea level, and temperatures exceeding 450 degrees Celsius. Venus did not end badly.
It ended slowly, and it ended completely. 1 billion years is the outer bound for complex life. For large animals, for ecosystems of the kind we recognize, for anything resembling the biosphere that currently covers this planet, the window is likely narrower. Some models place the end of habitability for multicellular life as early as 500 million years from now, as ocean temperatures exceed thermal tolerance for most organisms, and the carbon dioxide levels that plants require for photosynthesis drop below the minimum threshold. The carbon cycle begins to fail before the oceans begin to boil. The food web collapses from the base upward. Complex life ends not with fire,
but with quiet chemical failure. But the sun does not stop brightening when the last complex animal dies.
It continues. 10% per billion years. The dial keeps turning. There is a specific quality to this kind of ending that differs from all others. A meteor impact is something that happens to a planet from outside. A supervolcano is an expression of the planet's own interior geology. But the slow brightening of the sun is something different. It is the steady withdrawal of the conditions that made life possible in the first place, delivered by the same star that provided those conditions to begin with. The sun did not give us a stable climate and then try to take it away. It gave us a stable climate for a while, and the while was long enough for everything. Long enough for life to begin.
Long enough for complexity to arise. Long enough for something in the biosphere to become conscious and look up at the star that made it possible and start to ask questions. That is all the while we ever had. And it is already running out. Disaster does not always arrive. Sometimes it simply grows brighter, degree by degree, year by year, until the world beneath it can no longer hold itself together.
The sun's most profound change has not yet begun. Everything described so far, the gradual brightening, the slow migration of the habitable zone, the long erosion of the conditions that allow life, all of that unfolds while the sun is still, technically, in its youth, or rather in its middle age. The phase of stellar existence called the main sequence is defined by a single condition. The core is fusing hydrogen into helium. That condition has held for 4.6 billion years. It will hold for approximately another 5 billion years. And when it ends, the changes that follow will make everything that came before look like a prelude. The core has a finite supply of hydrogen.
When the hydrogen in the core is exhausted, when the fusion reactions that have been powering the sun for its entire main sequence life finally no longer have fuel, the core will change behavior entirely. It will not produce less energy gradually and fade. It will contract. The pressure that kept it stable against gravity will disappear, and gravity will win. The core will begin to collapse inward, and as it collapses, it will heat. This is not a paradox. Gravity does work as it compresses matter, and that work appears as heat. A collapsing core is a heating core, even as it runs out of the fuel that previously kept it warm. Around this contracting core, something else will happen.
A thin shell of hydrogen immediately surrounding the core. Hydrogen that was never hot enough to fuse while the core was burning will find itself newly adjacent to a core that is contracting and heating. The temperature at this shell will rise past the fusion threshold. Fusion will begin there. A shell of hydrogen surrounding the exhausted helium core will ignite and burn. The core shrinks. The shell burns. And the outer layers of the sun, above the burning shell, will respond in a way that seems counterintuitive. They will expand. This is the subgiant phase. It begins approximately 5 billion years from now, and it marks the end of the sun's time as a normal, stable, unremarkable main sequence star.
The sun will still be recognizable. It will not yet be wildly different in size or brightness from what it is today, but the internal restructuring will have begun. The architecture of the star will be changing, the core compressing, the shell burning, the outer layers swelling. For perhaps 1 billion years, the sun will exist in this intermediate state, a subgiant
brighter than the main sequence star it once was, larger, its surface cooler, but its total luminosity increasing as the burning shell drives more and more energy outward. The sun that rises over whatever remains of Earth in 5 billion years will be visibly, dramatically brighter than the sun of today.
The surface of the planet, if anything remains that could be called a surface, will be at temperatures that no life as we understand it could tolerate. But the core is still changing. As the helium core contracts and heats, it reaches a new threshold. At roughly 100 million degrees Celsius, helium nuclei can fuse. The process is called the triple alpha reaction because it requires 3 helium-4 nuclei, called alpha particles, to collide nearly simultaneously to produce a carbon-12 nucleus. This is a more demanding reaction than hydrogen fusion. It requires higher temperatures, higher densities, and a specific quantum mechanical coincidence. A resonance energy in the carbon-12 nucleus that is almost eerily well matched to the energies involved.
Had that resonance been even slightly different, the triple alpha reaction would be far less efficient, and the universe would contain almost no carbon. The carbon that makes up your body exists because a nuclear resonance in carbon-12 happens to be precisely positioned to make the triple alpha reaction work. When helium fusion ignites in the contracting core, the sun will have entered a new phase of its life. It will no longer be a star sustained by hydrogen burning at its center. It will be a star with a helium-burning core and a hydrogen-burning shell, a star that has moved off the main sequence permanently, entering the region of the Hertzsprung-Russell diagram that astronomers call the red giant branch. The word branch suggests something orderly, a diagram, a category.
The reality it describes is the opposite of orderly. The red giant phase is the most dramatic structural change a star like the Sun will undergo in its entire life. The outer layers, already expanded during the subgiant phase, will continue expanding, not gradually. The expansion accelerates as the helium-burning core drives more energy into the outer shells. The Sun's radius will grow and grow and keep growing. This is worth pausing on, not the mathematics of the expansion. Those come in the next chapter, but the conceptual reality of what it means for a star to swell. A star is not a rigid object.
It has no surface in the ordinary sense. What we call the solar surface, the photosphere, is the layer from which light can escape freely, a statistical boundary in a sphere of plasma. When the sun begins to expand, that boundary moves outward. The photosphere retreats from the core. Hundreds of thousands of kilometers of new volume appear. Plasma that was previously internal becomes, in a sense, the surface. The star grows not by adding material from outside. No material is being added, but by restructuring what it already contains, redistributing it over an ever larger volume. The sun that warms you today occupies a sphere about 1.4 million kilometers in diameter.
The sun that emerges from the red giant transition will occupy a sphere more than 100 times larger. The boundary of what was once the sun will reach outward past where the innermost planets orbit now. The consequences of this for those planets are not ambiguous. They are simply very far away in time. There is something disorienting about the arc of stellar evolution. We tend to think of old age as diminishment, a quieting, a fading, a gradual relinquishing of vigor. stars do the opposite. They grow more extreme. The red giant phase is not a peaceful decline. It is an expansion that swallows worlds. The violence is real.
It is simply governed by a clock measured in billions of years, and on that clock, it is already running. Aging does not always mean fading. Sometimes it means swelling beyond all previous bounds, consuming everything in reach before the final collapse. It is worth pausing on what drives this expansion. The expanding outer layers of a red giant are not gaining energy from the core. The core has stopped fusing hydrogen and is simply contracting. The energy that drives the outer envelope outward comes from the hydrogen-burning shell that has ignited around the exhausted core.
That shell is, in a sense, the sun burning through its reserves at an accelerating pace. The sun spending its remaining fuel more profligately than it ever has before, in a last phase of prodigious energy output that will last nearly 1 billion years. The sun will be brighter in its red giant phase than it has ever been before. It will be, by the standard of its own history, a more extreme version of itself. Larger, more luminous, shorter-lived in human terms, if not in stellar ones. But it will also eventually stop. The helium burning in the core, the triple alpha process that converts helium to carbon, will itself run out of fuel. The core will again contract, again heat. The outer layers will swell further. And then, over a period that plays out across tens of millions of years, the sun will begin to shed its outer envelope entirely. That shedding is its own chapter. But before it begins, the red giant must first do what red giants do: expand and take what falls within reach.
The red giant sun will not announce itself. There will be no single day when the people of some future civilization, if any exist, look at the sky and see a different sun. The expansion will be too slow for any generation to perceive it as change. The sun will simply be, decade after decade, slightly larger than it was, slightly redder, slightly cooler at its surface, as the same energy is spread across a greater area, even as the total luminosity climbs. No morning will feel like the last normal morning. The abnormal will become the new normal, again and again, as the star that formed the solar system slowly reaches outward to reclaim it. The sun's red giant expansion will reach its peak approximately 7.5 to 8 billion years from now. By that point, its radius will have grown to somewhere between 100 and 200 times its current size. The uncertainty in that figure matters. Whether the sun's radius at maximum expansion is 100 solar radii, or 150, or 200 is the difference between a star that merely scorches the inner solar system and one that physically engulfs it. Mercury will not survive. Mercury currently orbits at an average distance of approximately 0.38 astronomical units from the Sun, about 57 million kilometers. The expanding Sun, even at the conservative end of its projected radius, will reach well past this orbit.
Mercury will be absorbed, not struck, not shattered. Absorbed. The planet will find itself inside the photosphere of the expanding star, still orbiting, but now moving through the outermost layers of the sun's plasma. The drag will slow it. Its orbit will decay. It will spiral inward. Mercury will cease to exist as a separate object and become part of the sun's outer envelope.
This is a strange kind of death. Not the dramatic impact that ended the non-avian dinosaurs. Not the explosive death of a star in supernova. Mercury will die by inclusion, by being gradually incorporated into the body of the star it has orbited for 4.5 billion years. The end will be quiet. The planet will not shatter.
It will melt and disperse into plasma, its iron core and silicate mantle dissolved into the outer layers of a star that no longer fits inside its old boundaries. Venus follows. Venus orbits at 0.72 astronomical units, roughly 108 million kilometers from the Sun. At the upper end of estimates for the Sun's red giant radius, Venus too falls within the expanded photosphere. At the lower end, it sits just outside. Current calculations, based on the standard solar model, place Venus's absorption at roughly 7.8 billion years from now. Approximately 1 billion years after Mercury, in the final stages of the red giant expansion.
By this point, Venus will long since have been sterilized. Not that it hosts life now, given its current surface temperatures and atmospheric pressure, but any theoretical remnant chemistry on the planet will have been obliterated billions of years earlier as the Sun brightened through its subgiant phase. What the red giant expansion claims is not a living world. It claims a rock, a world-sized piece of silicate and iron that has been cooling in the dark for billions of years, now meeting the expanding star that warmed it once, and now consumes it. And then there is Earth. Earth orbits at 1 astronomical unit, 150 million kilometers from the Sun.
This distance is, by definition, the benchmark from which all other solar system distances are measured. It is also the distance that places Earth, currently, inside the Sun's habitable zone. Whether Earth will still be at this distance when the Sun reaches its red giant maximum is a question that does not have a clean answer. The answer depends on a physical process that makes the fate of the third planet genuinely uncertain. As the Sun expands into its red giant phase, it will lose mass, a great deal of mass. The red giant Sun will have a more tenuous gravitational grip on its outer layers and a stronger stellar wind. A continuous outflow of plasma will carry material away from the star into the surrounding space.
By the time the Sun reaches its maximum red giant radius, it may have shed somewhere between 20 and 30% of its total mass. Mass loss matters enormously for orbital dynamics. The gravitational force binding Earth to the Sun depends on the Sun's mass. If the Sun loses mass, its gravitational pull on the planets weakens. Weaker gravity means that orbiting bodies can maintain circular orbits at greater distances. They drift outward. A planet in a circular orbit around a star that gradually loses mass will itself gradually migrate outward, as though the gravitational well it is circling becomes shallower, and the orbit naturally expands to a larger radius.
For Earth, a sun that has lost 30% of its mass would imply an orbital expansion to roughly 1.4 or 1.5 astronomical units, well outside the expanded Sun's expected photosphere, even at the upper estimates for the red giant radius. This is the source of the debate. Does the orbital migration save Earth from physical absorption into the red giant Sun? The answer, worked out in the most careful published analysis of this question. A paper by Klaus-Peter Schroeder and Robert Conn Smith published in 2008 in the monthly notices of the Royal Astronomical Society, is probably not. The reason is tidal drag.
As the sun expands and its outer layers become more diffuse, a physical interaction develops between the sun's extended atmosphere and the Earth's orbit. The sun's photosphere is not a hard boundary. Its outermost layers are a sparse plasma, and as Earth's orbit carries it through, or near these layers, during the red giant maximum, the drag exerted by that plasma on Earth's motion will be enough, over time, to slow the planet's orbital velocity. A slower orbital velocity means a smaller orbit. Earth will spiral inward. Schrader and Smith calculate that the tidal interaction will be sufficient to overcome the outward orbital migration from mass loss, and that Earth will ultimately be dragged into the sun's outer layers during the final phase of the red giant expansion, approximately 7.6 billion years from now. This conclusion is disputed. Other researchers have pointed to uncertainties in the mass loss rate, the extent of the red giant's atmosphere, and the precise efficiency of tidal coupling. It is possible, not certain, but physically possible, that Earth's orbital migration from mass loss will be large enough to carry it beyond the reach of significant tidal drag, and that Earth will survive as a physical object, albeit a barren, airless, utterly uninhabitable one, orbiting a cooling remnant.
But the dispute is about the physical fate of a rock, the fate of anything that might be called a world, an environment, a surface, a possibility for life, is not in dispute at all. Long before the red giant expansion reaches Earth's orbit, the planet will have been unrecognizable for billions of years. The oceans will have evaporated within a billion years of now, as described in the previous chapter. The atmosphere will have been stripped by the increasing solar wind as the sun brightens and its coronal activity increases. The surface will be a bare, airless rock at temperatures that vaporize metal. What the red giant expansion encounters, if it encounters anything, will not be Earth in any meaningful sense.
It will be the last remnant of a planet that was once the only known home of life. A record of what was here, before the star that made it possible began the expansion that concludes its own story. The solar system is dying. Not quickly, not dramatically. It is dying the way the sun has always done everything. Slowly, continuously, without pause, following physics that does not deviate and does not make exceptions. The question was never whether the sun would expand. The question is, what happens to the third rock when it does?
The question was never whether the sun would expand. The question is what happens to the third rock when it does. And to understand that, we have to go deeper first. Deep into the structure of the star itself. Into the physics of what happens when the fuel begins to run out. Right now, in this moment, the sun is balanced. Two forces in perfect, ancient equilibrium. Outward, the pressure of nuclear fusion, hydrogen nuclei colliding at 15 million degrees Celsius, releasing energy that pushes the star's layers outward against their own weight. Inward, gravity, the accumulated mass of 2 × 10 to the power of 30 kilograms, pulling everything toward the center.
A shell of hydrogen that had not yet been consumed, now suddenly hot enough to fuse. The shell burns furiously, far more intensely than the core ever did, and the energy released by that shell pushes the outer layers of the sun outward. The sun begins to swell, slowly at first, imperceptibly. Over hundreds of millions of years, the radius expands. The surface cools as it stretches across a larger area. The color shifts from the yellow-white of a main sequence star toward the deep orange-red of something vast and cooling. The sun becomes a red giant. This phase will last approximately 1 billion years in total, though its most dramatic expansion happens in the final hundreds of millions of years. 1 billion years.
Set beside the entire current age of the universe, which is approximately 13.8 billion years. 1 billion years is not a small number. It is nearly a tenth of all cosmic time that has elapsed since the Big Bang. But set beside the time the sun has already burned, another 4.5 billion years, it is a final chapter. A long one, but a final one. During the red giant phase, the sun's luminosity will climb to somewhere between 2,000 and 3,000 times its current output. 2,000 times.
If you wanted to hold that number in any kind of human frame, imagine replacing every light source on Earth, every lamp, every screen, every city, every fire, and multiplying them by a factor that makes them irrelevant. The scale cannot be communicated by analogy. It can only be stated. 2,000 times brighter for 1 billion years. But before the outer layers complete their expansion, something else happens. Something buried in the core. Something the universe keeps entirely hidden from the outside. Deep in the contracting helium core, under temperatures that have risen to roughly 100 million degrees Celsius, a threshold is crossed. Helium nuclei, which are heavier and more resistant to fusion than hydrogen, begin to collide with enough energy to merge.
3 helium nuclei combine to form a carbon nucleus. This is called the triple alpha process, and the moment it ignites, it does not ignite gently. In a degenerate core, the kind of compressed, crystalline stellar material that forms in the red giant, the physics of ignition behaves differently than in normal gas. In normal gas, when temperature rises, pressure rises with it. The gas expands, and the expansion cools the reaction. A natural thermostat. But in a degenerate core, pressure does not depend on temperature in the same way. When ignition happens, the temperature surges, but the pressure does not rise. The core does not expand. The reaction accelerates without limit. In a matter of seconds, the energy released approaches the luminosity of the entire Milky Way, not the sun.
The entire galaxy, 400 billion stars, all of their combined light. That is the power of the helium flash, released in seconds. And from the outside, nothing changes. The outer layers of the sun absorb all of it. Every joule, every erg of that galaxy-scale energy release is swallowed by the star's own envelope before a single photon can escape. The helium flash happens in total secrecy. the most violent event in the Sun's biography passes without announcement.
That the universe provides some warning proportional to the magnitude of what is happening. But the helium flash suggests otherwise. The most explosive transition in the Sun's 10 billion year life will be invisible. Think of what it means to be present in a solar system during that moment. If anything were alive on any surviving surface in that future solar system, or in orbit around some distant world watching the Sun, they would see nothing. The Sun's surface brightness might flicker by amounts too small to distinguish from normal variability. The helium flash lasts seconds. Its effects are absorbed in milliseconds by the overlying stellar material. The most violent second in the Sun's biography would be indistinguishable from an ordinary second.
Just a star, hanging in the sky, burning with the same dull orange glow it had the moment before. There is something in that observation that is harder to shake than the numbers themselves. The disconnection between internal catastrophe and external appearance. The universe's capacity for enormous internal transformation that registers as nothing on the outside. Stars are not the only things that work this way. But the helium flash is one of the most extreme examples. A galaxy's worth of energy. Invisible. Gone into the stellar envelope, leaving no trace visible from outside. The core rearranges. The degenerate material is disrupted by the heat. Normal gas physics resume. The runaway reaction stabilizes.
Helium begins to burn steadily in the core, and a shell of hydrogen continues to burn outside it. The Sun enters a calmer second phase of its giant existence. But this stability is borrowed time. As the helium burns down, the core fills with carbon and oxygen. The same sequence begins again. Core contracts. A helium shell ignites around it. A hydrogen shell burns further out. The outer layers swell further still. The Sun climbs what astronomers call the asymptotic giant branch, the final, most extreme phase of stellar expansion. The outer layers, now barely bound by gravity, extend to a radius somewhere between 100 and 200 times the Sun's current size. 100 times the current solar radius is approximately 69 million kilometers.
Earth's current orbital distance from the Sun is approximately 150 million kilometers. Even at the conservative estimate of 100 solar radii, the Sun's surface would extend roughly halfway to where Earth currently orbits. At the upper estimate of 200 solar radii, it would reach past Earth's current position entirely. Mercury will be gone. Venus will be gone. Whether Earth survives, even as a bare, airless rock, is a question that depends on forces pulling in opposite directions. A question we will return to. But for this moment, stay with the scale. A star 200 times its current diameter. A surface temperature of 3,000 to 4,000 Kelvin, cooler than the Sun today, which is why it appears red.
A luminosity 2,000 to 3,000 times current output. A world 8 minutes of light away from us, transformed into something that engulfs what we think of as the inner solar system. Not a metaphor, a physical reality, a transformation already written into the laws of physics
waiting for time to execute it. And on the surface of the Earth, long before the Sun reaches its maximum radius, long before any of the orbital questions become relevant, the consequences will have already been total. Surface temperatures exceeding 1,000 degrees Celsius. Rock flows in slow, dark rivers. The atmosphere, if any trace remains, is a thin poison of vaporized minerals. No ocean, no soil, no shadow. This is the red giant phase, a slow catastrophe. A billion-year process that dismantles the inner solar system 1 degree at a time, unhurried, inevitable. Already underway in the sense that the physics that will produce it are already in motion, ticking forward at the rate of 620 million tons of hydrogen per second. Consider what it means that we can describe all of this. Every step of the sequence, from the first signs of hydrogen exhaustion to the asymptotic giant branch expansion, is not speculation. It is derived from stellar physics that has been tested across thousands of stars at different stages of their lives. We have observed stars in every phase of this process. Stars burning quietly on the main sequence like our Sun. Stars in the subgiant transition, beginning to swell.
Stars fully expanded into red giants, their light deep orange, their outer layers barely held by gravity. Stars in the helium-burning phase, temporarily stabilized. Stars ascending the asymptotic giant branch, shedding their outer layers in rhythmic pulses. We have seen all of it, not in sequence, because no human life is long enough to watch a single star complete this journey. But across thousands of stars we have assembled the complete picture. The life of a sun-like star is not a mystery. It is a sequence we understand well enough to calculate. And the calculation tells us something that is both precise and enormous. The sun has a trajectory. It has always had a trajectory.
The same trajectory that every star of similar mass follows, modified only by the exact details of composition and rotation. There is no version of events in which the Sun remains on the main sequence indefinitely. There is no intervention, no stabilization, no alternative physics. The Sun is moving through its life on a timescale that dwarfs human comprehension, but it is moving, and the destination is the same. Always the same. We are currently living on a planet orbiting a star at middle age. Not young, not dying. Middle age. The Sun has burned long enough that the hydrogen at its core has been partially depleted. It has brightened already by perhaps 20 to 30% since its formation.
Every morning, the star that rises is slightly different from the star that rose a billion years before. Not by any amount a human observer could detect in a lifetime, but different. Growing slowly, incrementally, irreversibly brighter, accumulating the consequence of its own energy. The Sun does not know this. The Sun does not experience its own trajectory. It simply continues, converting hydrogen to helium, radiating energy outward, moving without intention toward the inevitable end of this particular phase of its existence.
There is a question that researchers have approached with genuine scientific seriousness and genuine uncertainty. Will Earth survive? It sounds almost optimistic as a question, as though the answer might be yes, and that yes might matter. But the question is worth examining carefully, because the answer reveals something important about the physics and about the nature of what we mean by survival. As the Sun sheds mass during the red giant phase, its gravitational hold on the solar system weakens, The stellar winds that strip material from the sun's expanding outer layers are substantial. Over the full red giant phase, the sun may lose approximately 30% of its total mass. Gravity is proportional to mass.
A star with 30% less mass exerts 30% less gravitational pull on the objects orbiting it. And when the gravitational pull decreases, orbits expand. Planets drift outward. The relationship is straightforward. If the sun loses mass slowly enough, the planets migrate outward adiabatically, maintaining their orbital shapes while shifting to larger radii. Earth's orbit, currently at 1 astronomical unit, could migrate outward to approximately 1.5 astronomical units. Possibly further, depending on the exact rate of mass loss. 1.5 astronomical units. Mars currently orbits at roughly 1.5 astronomical units. In theory, Earth could end up roughly where Mars is today, sitting outside the expanding solar envelope, surviving as a physical object. This is the case for survival.
And it is not dismissed by mainstream planetary science. It is taken seriously. The orbital migration is real. The mass loss is real. The physics is correct. But there is a competing effect, and it pulls the other way. As the sun expands, its outer atmosphere becomes enormous and diffuse. The outermost layers of the red giant are barely held together. Densities that would count as a laboratory vacuum on Earth. Vast, thin, tenuous. Earth, as it orbits through the region where the sun's outer atmosphere begins to extend, encounters this material.
And across millions of years, even very slight drag has enormous cumulative consequences. This drag removes energy from Earth's orbit. An orbit that loses energy shrinks. The planet moves inward rather than outward. Additionally, there is a tidal interaction. The sun, expanded to enormous size, is no longer a point mass. Its near side exerts more gravitational pull on Earth than its far side. This differential, the tidal force, creates a torque on Earth's orbit, a torque that transfers angular momentum from Earth to the sun, and in doing so, causes Earth to spiral inward. Klaus-Peter Schroeder and Robert Conan Smith worked through the full calculation in 2008.
They modeled the orbital migration driven by mass loss, and separately modeled the drag and tidal forces acting against it. They ran the numbers forward through the sun's full red giant phase. Their result was that the tidal drag overcomes the outward migration. Earth does not escape. In the final 500 million years of the red giant phase, Earth's orbit decays. Earth falls inward into the solar atmosphere. The drag accelerates. The spiral tightens. Earth is absorbed, not dramatically, not in a single flash, but over millions of years of decelerating spiral. Earth sinks into the increasingly dense outer layers of the dying sun, heating, ablating, breaking apart, and eventually merging with the stellar material. The distinction matters physically. Earth is not burned from a distance.
The planet that formed here, that accumulated from the same cloud of gas and dust that formed the sun itself, 4.5 billion years ago returns, not through any mystical process, just gravity and drag and time. But even the optimistic scenario, where the orbital migration succeeds and Earth drifts to 1.5 astronomical units and survives as an object, does not constitute survival in any meaningful sense. Because the surface of Earth will have been dead for hundreds of millions of years before any of this is decided. The question of whether Earth survives is a question about rock, not about anything on the rock, not about the thin, wet layer on the surface where biology happened to organize itself.
That layer is gone long before the orbital fate is settled. Long before the sun becomes a red giant, the oceans are gone. Long before the sun becomes a red giant, the atmosphere is stripped. Long before the orbital mechanics tip one way or another, Earth's surface is a field of cooling and remelting lava. Whether that field of lava then falls into the sun or drifts past it as a naked rock is, in the most honest sense, irrelevant to the story of life. It is a question with no witness. And perhaps that is the part worth sitting with. Not the physics. The absence of the witness. We build systems to understand the universe. We train instruments. We send probes. We write equations.
We calculate the orbital mechanics of a planet 5 billion years from now with genuine precision. And the precision is real, and the science is careful, and the results are meaningful. But there is a gap between the precision of the calculation and the presence of anyone to receive it. Schroeder and Smith's paper is, among other things, the most rigorous calculation ever made of an event that no human mind will ever observe. The exit window closes, and usually no one is watching when it does. There is a tendency, when thinking about planetary fates on billion-year timescales, to reach for meaning, to look for the lesson, to find the reason these calculations matter beyond the intrinsic interest of the physics. And the search is not wrong.
But the answer is not what most people expect. The calculation matters not because it tells us we should be afraid. The sun's fate in 5 billion years is not a threat that requires a response. It matters because it places the present moment inside a context that nothing else provides. Right now, Earth has liquid water. Right now, the atmosphere holds oxygen in concentrations that allow complex respiration. Right now, the magnetic field deflects the solar wind away from the surface. Right now, the moon stabilizes the axial tilt that moderates the seasons. Right now, the sun burns at a luminosity that keeps the average surface temperature in the range where water is liquid rather than vapor or ice. All of these conditions are temporary.
Each one has a finite duration. Each one will end on its own timescale, before or after the others. The calculation of Earth's orbital fate in the red giant phase tells us that even the survival of the planet's physical form is uncertain, that there is no safe version of the long future for Earth, that the question is not whether something will change, but only what will change first. Knowing this does not produce despair. Not, at least, if you sit with it long enough. It produces something quieter, a kind of orientation, an understanding of the scale within which the present exists.
Before the red giant, before the orbital fate is decided, before any of the billion-year timelines become relevant, something quieter happens. The oceans end. They end not with a dramatic event, not with an asteroid, not with a stellar eruption. They end because the sun is already changing. Has always been changing, has been growing slightly brighter since the day it formed. Every billion years, the sun's luminosity increases by roughly 10%.
This has been happening for 4.5 billion years. It is why scientists believe early Earth, under a sun 30% dimmer than today, was not frozen, though the question of how it stayed warm enough for liquid water is still debated. It is why the sun today is already brighter than the sun that warmed the Cambrian seas. And it is why in approximately 1 billion years, the sun will be bright enough to tip Earth's climate past a threshold from which there is no return. The mechanism is called the moist greenhouse effect, and it works like this. As global temperatures rise, more water evaporates from the ocean surface. Water vapor is a potent greenhouse gas. More water vapor traps more heat.
More heat produces more evaporation. The cycle runs forward. On short timescales, this cycle is stabilized by other feedbacks. Clouds, ocean circulation, the chemical weathering of silicate rocks, which pulls carbon dioxide from the atmosphere. These feedbacks have kept Earth's temperature roughly stable for billions of years. But as the sun's output crosses a certain threshold, the feedbacks are overwhelmed. The evaporation cycle wins. Water vapor accumulates in the atmosphere faster than it can be removed. The stratosphere becomes saturated with water. Ultraviolet radiation from the sun begins to break apart water molecules in the upper atmosphere. A molecule of water, H2O, is split into hydrogen and oxygen by high-energy photons. The oxygen remains, reacting with surface minerals.
But hydrogen, the lightest element, has a thermal velocity high enough that a significant fraction of it escapes Earth's gravitational field entirely. It drifts into space, and it does not come back. Over millions of years, the hydrogen content of Earth's water is lost to space. Without hydrogen, there is no water. The oceans thin. They shrink from their edges inward. The shallow seas are first, then the continental margins, then the deep ocean basins, emptying over timescales too long for any single observer to register, but too short for geology to misremember. Within approximately 1 billion years from now, Earth's oceans will no longer exist. The planet's surface will be dry.
The blue color that makes Earth visible from space, that gives it the name the pale blue dot, will be gone. Earth from orbit will look like Mars, or worse. Mars at least has ice at its poles. With the oceans gone, the carbon cycle collapses. Carbon dioxide, which is drawn out of the atmosphere through chemical weathering of rocks and dissolved into the ocean, has nowhere to go. It accumulates. Temperatures climb further. The surface heats past what any multicellular organism can tolerate. The end of the oceans is the end of the biosphere as we understand it. Not immediately, not on a human timescale. But on the timescale of the planet, one transition follows the other with inevitability. Complex life ends. Animals, plants.
Everything visible to the naked eye, everything large enough to have a nervous system, gone, not killed in a single event. Displaced, one habitat at a time, as the envelope of survivable conditions shrinks. The last forests do not burn, they dry. The last ecosystems do not collapse in drama. They thin and thin further and thin again, until the definition of the word ecosystem no longer applies to what remains. But life does not end when complex life ends. Not immediately. Microbial life has existed on Earth for approximately 3.5 billion years. It existed before the oceans were oxygenated, before the atmosphere had free oxygen, before any multicellular organism evolved, and it has survived every mass extinction that complex life has endured since the Cambrian.
Certain microorganisms alive today live in conditions that would kill a human being in seconds. Hydrothermal vents at the ocean floor, where water reaches temperatures above 300 degrees Celsius under pressure that prevents boiling. Acidic hot springs with pH values approaching 0. Rock formations, kilometers underground, where organisms metabolize nothing more than the slow chemical reactions of mineral interfaces and receive no sunlight, no nutrients from the surface, nothing but heat and chemistry. These are not exotic, isolated exceptions. They are part of what Earth's biosphere actually is. A biosphere that extends from the surface down through kilometers of crust into heat and pressure and darkness. As the surface becomes uninhabitable over the next billion years, the deep biosphere may persist. Retreating deeper, moving further from the hostile surface.
Living in rock cracks, living in hydrothermal gradients, living at temperatures that would denature the proteins of any surface organism. Models suggest that microbial life could persist in the subsurface for perhaps 2 to 3 billion years after the surface biosphere ends. 2 to 3 billion years. Which means that the last living things on Earth may not die until the sun has already entered its red giant phase. The last living organisms on Earth may survive long enough to exist inside a star, not knowing it, not capable of knowing it, just metabolizing slowly in the deep rock, as the world above them transforms into something unrecognizable. Now hold a comparison. Human civilization in its recognizable form, agriculture, cities, writing, accumulated knowledge, spans approximately 10,000 years. 10,000.
The window during which complex life on Earth is possible, from now until the ocean evaporation threshold, is approximately 800 million to 1 billion years. The ratio is roughly 1 to 80,000. Human civilization, against the remaining window of complex life, is a fraction so small that the word fraction no longer captures it. It is a line too thin to draw on any diagram, a duration too brief to mark on any geological timescale. A window inside a window inside a window, each one smaller than the last. We exist inside a configuration. A precise, temporary, accidental configuration of atmospheric chemistry and magnetic shielding and orbital radius and liquid water.
A configuration that allows the kind of chemistry that organizes itself into cells, and cells into organisms, and organisms into things that ask questions about their own existence. This configuration was not created for us. It will not be maintained for us. It is a transient state of a planet orbiting a star in the middle of its life,
and it will not last much longer on astronomical timescales. The window is open, but the window is closing, slowly, across a timescale that makes the closing invisible from inside a human life, but closing measurably, reliably, with the same precision that calculates planetary orbits and stellar evolution. The last oceans will evaporate, not because something goes wrong.
Because this is what happens to oceans on a planet orbiting an aging star. This is what always was going to happen, and knowing it changes something, though it is difficult to say exactly what. The oceans have existed on this planet for approximately 4 billion years. They formed from water delivered by asteroids and comets in the early solar system, and from outgassing of the young crust. They have survived meteor impacts. They have survived snowball Earth episodes when ice sheets extended to the tropics and the surface was almost entirely frozen. They have survived the oxygenation event when cyanobacteria exhaled so much free oxygen that it poisoned the existing biosphere and transformed the atmosphere entirely. They have outlasted every extinction.
They have been here longer than any mountain range currently standing, longer than any ocean basin in its current configuration. They will evaporate on a timescale that has no precedent in any event that has occurred during the ocean's existence. Not suddenly. Over tens of millions of years, the edges recede, the basins shallow, the average salinity rises as water volume decreases. The remaining liquid grows hotter and more hostile. And eventually, the last tide turns on a sea that is not yet fully gone, but will never be replenished. There is a particular weight to this thought when you consider what the oceans have carried. Not metaphorically. The literal cargo. 4 billion years of dissolved chemistry. The raw materials for the first self-replicating molecules.
The dissolved minerals and organic compounds that allowed the first cells to build walls and capture energy. The currents that transported nutrients and heat across the global surface and made complex ecosystems possible. The medium through which life's earliest experiments in multicellularity played out. The oceans did not just contain life. They were the environment that made life possible in the first place. They are the medium and the origin, and they are going to end. This is the part of the timeline that is most difficult to absorb. Not the red giant, not the white dwarf, not the billion-year cooling of a dead star, the loss of the oceans. Because the oceans are not distant or abstract, they are here, right now, covering 70% of the surface.
Generating the oxygen in every second breath, regulating the temperature of the entire climate system, and in approximately 1 billion years they will be gone. 1 billion years is a long time by any human measure, but it is not infinite. It is a number, a finite, specific, calculable duration. And on the other side of it, there will be no blue planet.
After the red giant phase ends, after the outer layers have reached their maximum extent, and the last helium has been converted to carbon and oxygen, and the core has no remaining fusion pathway, the sun enters its final active chapter. And it does not end with an explosion. It ends with a breath. In the final 100,000 years of the red giant, the sun's outer atmosphere becomes increasingly unstable. Thermal pulses from the helium shell burning below drive waves of material outward.
The outer layers, already barely bound by gravity, are expelled in successive shells. Each pulse sends another wave of gas and dust moving outward into space at velocities of 10 to 30 kilometers per second. 10 to 30 kilometers per second.
That is 30 to 90 times the speed of sound in air. Fast enough to cross the distance from Earth to the Moon in a few hours, and these shells expand silently outward into the surrounding space, growing, cooling, spreading. As the outer layers are stripped away, the hot core of the Sun is exposed. The core is dense and compressed, and enormously hot, initially exceeding 100,000 Kelvin. From this exposed core, a new stellar wind erupts, faster than the expelled shells, moving at hundreds of kilometers per second. This fast wind overtakes the slow-moving shells already drifting outward. It collides with them. It compresses the inner edges of the expanding shells. It sculpts them,
pushes them into complex structures determined by the star's magnetic field, its rotation, and the geometry of the mass loss over time. The result is what astronomers call a planetary nebula, a name chosen in the 18th century by observers who, through small telescopes, saw fuzzy disk-like objects that reminded them of the planets Uranus and Neptune when imaged under poor conditions. The name has nothing to do with planets. It has everything to do with misidentification and the accident of history. But it has lasted, and it has a certain beauty, despite its imprecision. Because what planetary nebulae actually are is something more remarkable than planets. They are the exhaled atmospheres of dying stars. They are the released interiors of objects that burned for billions of years.
They are the material that will seed the next generation of stars and planets, drifting through space until some gravitational disturbance brings it together again into something new. The light we see in a planetary nebula comes from the expelled gas being ionized by ultraviolet radiation from the hot central star. Oxygen atoms, stripped of 1 or 2 electrons, emit the blue-green light that makes the Cat's Eye Nebula glow. Hydrogen emits red. Nitrogen emits deeper red and crimson. Each element contributes its characteristic signature. Each color is a map of the stellar composition. The Cat's Eye Nebula, NGC 6543, 3,000 light-years away. The Helix Nebula, NGC 7293, 650 light-years away.
The Ring Nebula, M57, 2,300 light-years away. These are not abstract illustrations. They are not artists' impressions. They are real objects. Real expelled stellar atmospheres. Real hot cores at their centers. Each one a star that completed this transition between roughly 1,000 and 10,000 years ago. Still expanding, still glowing, still carrying the chemical record of a life spent fusing hydrogen into helium into carbon. When you look at the Helix Nebula, you are seeing the future of the Sun. The central star at the heart of the helix is a white dwarf. Its expelled atmosphere is still moving outward. The shells are still expanding, growing thinner and cooler, and will eventually disperse into the interstellar medium over tens of thousands of years.
The Sun will produce something similar. Its expelled material may span several light-years. It will glow for roughly 10,000 years as the hot central white dwarf ionizes the surrounding gas. Then it will fade, the gas will cool, the structure will become invisible, and the white dwarf will be left alone. The white dwarf that remains will be roughly the size of Earth, possibly slightly smaller. This requires a moment. The Sun today is approximately 109 times the diameter of Earth. It contains enough mass that 1,300,000 Earths could fit inside it. After the red giant mass loss and the expulsion of the planetary nebula, approximately 60% of the original mass remains.
This mass, the equivalent of roughly 600,000 Earths, compressed into a volume roughly the size of Earth. The density follows from the mathematics. 1 teaspoon of white dwarf material weighs approximately 15 tons on Earth. Not metaphorically. Actually, 15 tons. A medium-sized car weighs around 1.5 tons. 1 small spoonful of what the Sun will become outweighs 10 cars. And inside this object, nothing is burning. There is no fusion, no nuclear reaction, no energy source of any kind. What the white dwarf possesses is stored heat, the thermal energy accumulated over 10 billion years of nuclear fusion, compressed into a small, dense object that is extremely good at retaining heat because it is so dense that radiative cooling is very slow.
The white dwarf is cooling, has been cooling since the moment it formed, will continue cooling for longer than the universe has currently existed. At its formation, the surface temperature may exceed 100,000 Kelvin. Over billions of years, it cools toward tens of thousands of Kelvin. Over hundreds of billions of years, toward thousands. Over trillions of years, toward hundreds. And eventually, in theory, toward the temperature of the surrounding space. At that point, the white dwarf becomes a black dwarf, a cold, inert, dark object. Carbon and oxygen, crystallized under immense pressure, forming a structure similar to a diamond on a scale comparable to a planet. Silent, lightless, still. No black dwarf has ever been observed. None can exist yet.
The universe is approximately 13.8 billion years old. The cooling time required to produce a black dwarf exceeds 1 quadrillion years, 1 million billion years. The universe is not old enough by a factor of roughly 70,000. The oldest white dwarfs in existence today, ancient objects produced by the first generations of stars, are still warm, still cooling. Will still be cooling long after any star currently forming has completed its entire life cycle and become a white dwarf of its own. There is an aspect of white dwarfs that the universe has revealed only recently through careful spectroscopy. Many white dwarfs show the chemical signatures of elements heavier than carbon and oxygen in their atmospheres: calcium, iron, magnesium.
Elements that should sink quickly in a white dwarf's high-gravity atmosphere, and yet they persist. The explanation is accretion. These white dwarfs are accumulating material from their own surrounding debris, rocky fragments, asteroid-like bodies. The remnants of planetary systems that survived the red giant phase, then broke apart under gravitational stresses, raining their material down onto the compact stellar remnant. These are called polluted white dwarfs. The pollution is the residue of worlds. Calcium from the crust of a former planet, iron from the core of a former moon, silicon from ancient rock that once orbited a living star. The chemical analysis of polluted white dwarfs has become one of the most powerful tools for understanding planetary compositions.
By reading the pollution,
Scientists reconstruct what the accreted material was made of, what kind of world it was. Whether it had a differentiated iron core, whether it was volatile rich or volatile poor. It is in the most literal sense reading the remains. The white dwarf holds the chemical signature of the system it once sustained. Not as a memorial, not as a record preserved intentionally, just as chemistry. The elements were there, the gravity collected them, the evidence remained. The solar system will not be entirely erased. The outer planets, Jupiter, Saturn, Uranus, Neptune, their orbits expanded by the sun's mass loss, will survive. Their composition will be altered. Their moons may be disrupted. Their atmospheres may be stripped by the red giant wind.
But their bulk will persist, circling the white dwarf on expanded orbits, growing slowly colder as the central light fades. And the debris of the inner solar system, the material of Mercury and Venus and Earth, if Earth falls in, the asteroids, the comets, may contribute to the pollution of the sun's white dwarf form. The sun will carry, in its atmosphere, traces of what it once lit, the chemistry of the planets it once warmed, dust from the inner solar system, the solar system that no longer exists as such, accreting slowly onto the dense remnant of the star that once burned at its center. This is how the sun ends, not with the silence of nothing, with the long silence of cooling.
A silence that lasts longer than the universe has been old, punctuated only by the slow drift of rocky debris falling into a dead star. It is worth pausing on what the white dwarf is in the most fundamental sense. It is a stellar core, the object that, for 10 billion years, provided the gravitational center of the solar system. The object that every planet, every asteroid, every comet, every grain of dust in the system orbited. The thing that held the system together. Now it is a remnant. Dense, hot, slowly fading, still at the center, still orbited by whatever remains, but no longer providing the heat that made chemistry happen on the surfaces of the inner planets.
No longer maintaining the energy gradient that drove weather and ocean circulation and biological metabolism. No longer burning. Jupiter and Saturn will orbit it, cold and dark. Their great storm systems stilled, their atmospheres thinned by the passage of the red giant wind. They will continue their orbits on expanded radii, moving more slowly through a solar system that is no longer lit. Uranus and Neptune will orbit it, further out, colder still. Their moons may drift, some may be captured, some may escape entirely. The outer solar system, which was always cold by inner solar system standards, will become cold in a way that has no comparison in the history of the system. And the white dwarf itself will cool, degree by degree, century by century, millennium.
From the blinding ultraviolet heat of newly exposed stellar core, through the temperatures of ordinary stars, through the temperatures of cool red dwarfs, down toward the background temperature of the universe. The process cannot be completed in the current age of the universe. The background temperature of the universe is currently about 2.7 Kelvin, the remnant of the Big Bang.
Wait long enough, and the universe will be a place populated almost entirely by slowly cooling white dwarfs, by cold neutron stars, by black holes evaporating through Hawking radiation on timescales so vast that they reduce the current age of the universe to a rounding error. The sun's white dwarf will still be cooling then, still drifting through a changed and darkened universe, still carrying the chemical residue of the inner solar system, still orbited, perhaps, by the frozen remnants of the gas giants. We do not know what the universe will be like on those timescales. We know the physics. We know the timescales the physics implies.
But whether any structure will exist by then that could observe or record, or in any way register the cooling of the solar remnant, is a question that physics cannot answer. It touches the edge of what the word existence means. What we know is this: the sun will end. It will not end with silence. It will end with a long, slow, cooling silence. A silence that begins when the planetary nebula fades. A silence that the outer planets will orbit within. A silence that deepens as temperature drops. A silence that, in the complete absence of any witness, will look identical to the silence that preceded the sun's formation. Before the sun existed, there was a molecular cloud, cold gas, drifting, slowly condensing.
After the sun's white dwarf finishes its cooling, there will be a black dwarf, cold carbon, drifting, slowly losing the last trace of its stored heat. The beginning and the end resemble each other, cold and dark and patient. Waiting, if waiting is the right word, for whatever comes next. And then there will be no more sunrises, only a faint white ember, drifting through the dark.
And then there will be no more sunrises, only a faint white ember, drifting through the dark. But the sun does not take everything with it when it dies. Beyond the scorched inner system, beyond the orbit where Earth once turned, the outer planets endure. Jupiter, Saturn, Uranus, Neptune. They are too far, too massive, too cold to be swallowed. The red giant's atmosphere will expand past the inner worlds, and then, in a geological eye blink, recede.
When a star loses mass, gravity relaxes. This is not a metaphor. It is basic orbital mechanics. Every planet in the solar system responds to that change with precision. The orbits loosen, like a fist slowly opening, each world drifting outward as the gravitational tether that has held it in place for billions of years becomes fractionally weaker. Jupiter, already the largest planet in the solar system, containing more mass than all the other planets combined, will migrate outward by perhaps 2 to 3 times its current distance from the Sun. Saturn will follow. Uranus and Neptune will follow Saturn. The gas giants will continue their slow patrol of a dimming, quieter system, circling a star that is no longer a star in any meaningful sense.
It is a strange kind of survival. These worlds will orbit something that gives them almost nothing. No warmth capable of melting ice. No ultraviolet radiation sufficient to drive meaningful chemistry at the surface. No light bright enough to cast a shadow across their moons. They will keep moving,
because moving is what planets do. They will trace their vast ellipses through the dark with the mechanical patience of things that do not know they are waiting for nothing. Patience is not a property of planets. It is something we project onto them. But the projection is hard to resist when you consider the sheer duration involved. Jupiter will continue orbiting the white dwarf for tens of billions of years after the Sun's death.
Saturn's rings, already ancient, will persist in some form for longer still. The universe does not require purpose as a condition for continuation. Things continue because the conditions that would stop them have not yet arrived. Further out, the situation is stranger still. The Kuiper belt, the ring of frozen bodies beyond Neptune's orbit, will disperse. The objects that make up that distant reef of ice and rock have always been held loosely, governed by a sun that was already faint at that distance. As the sun shrinks into a white dwarf, its reduced mass shifts the gravitational arithmetic of the outer system.
Some Kuiper belt objects will drift inward on unstable orbits, falling toward the white dwarf and eventually being torn apart by its intense tidal forces or vaporized by its surface heat. Others will be flung outward, escaping the solar system entirely, joining the sparse population of rogue objects that drift between stars. And beyond even that, the Oort cloud, the vast spherical halo of comets that surrounds the entire solar system at distances measured in light years, will begin to dissolve. The Oort cloud is not a dense structure. It is more like a vast diffuse fog of frozen bodies, each one separated from its neighbors by enormous distances, each one barely bound to the sun by the faintest gravitational thread.
The comets in the Oort cloud have always been hovering at the edge of the sun's gravitational reach. Once that reach contracts, they will slip free. Trillions of frozen objects, each one a remnant of the solar system's earliest formation, will drift off into interstellar space. They will not explode. They will not burn. They will simply leave, silently, and over millions of years, and no one will notice. There is something in this that resists easy description. The solar system will not end with a single catastrophic event. It will unravel gradually, at the edges first. The outermost things will go quietly, one by one, pulled away by nothing more dramatic than the slow arithmetic of gravity minus mass.
The sun's death will propagate outward like the last echo of a sound. Not loud, not sudden, but persistent and complete. Jupiter will still be there, still spinning, still wrapped in its bands of cloud and storm, its great atmospheric structures cycling through patterns that have endured for longer than complex life has existed on Earth. But the storms will be different then, driven entirely by internal heat, since there will be no solar energy worth mentioning at that distance. Jupiter has always generated its own warmth from the slow gravitational contraction of its interior. That internal warmth will remain long after the sun is gone. It will outlast the red giant phase. It will outlast the planetary nebula.
It will still be releasing heat from its own interior billions of years after the sun has become a white dwarf cooling in the dark. Its moons, Europa, Ganymede, Callisto, and perhaps others, may still harbor liquid water beneath their ice, not because of the sun, which never warmed them much, even at its peak, but because of tidal flexing from Jupiter's immense gravity and residual heat from the planet's interior. Life, if it ever existed in those hidden oceans,
might persist far longer than any surface life on Earth. The conditions for biology are not exclusively solar. They never were. The requirement is energy and liquid water. And both of those things can exist in places that the sun.
But life requires time as much as it requires the right chemistry. And in that dimmed, cold outer system, circling a white dwarf that gives almost nothing, time will stretch on without obvious purpose. The outer planets will keep their orbits. They will keep their moons. They will keep whatever biological or chemical secrets their interiors hold, and none of it will matter to anything, because there will be no one in that system left to observe it, to wonder about it, to assign it meaning. Survival without witness is just persistence. The outer solar system will persist for a very long time, moving in slow, patient circles around a cooling ember, in a darkness that is almost, but not quite, complete.
The distinction matters less and less as the light fades.
The white dwarf that remains after the sun's death will be approximately the size of Earth. Let that settle for a moment. A star that once contained more than 1 million Earths by volume. A star so large that if you placed it at the center of our solar system, its surface would extend past the orbit of Mercury, compressed down into something no larger than the planet you are standing on right now. Its diameter will be roughly 12,000 kilometers. Its mass will still be more than half the mass of the current sun. A teaspoon of its material would weigh approximately 5 tons. The density is not intuitive. It does not map onto any human experience of weight or substance.
It is simply a number that exists beyond the edge of what the imagination can genuinely process. The white dwarf will be hot at first, extremely hot. Its surface temperature when newly formed may exceed 100,000 degrees Celsius. It will emit light, but it will be a strange light. Intense, blue-white, ultraviolet heavy. It will illuminate nothing in the way the sun once did. There will be no warmth of the kind that allows liquid water.
It is the residual emission of a body releasing the energy it stored during its lifetime as a star, and there is no mechanism inside it to replace that energy once it is gone. There is no nuclear fusion happening inside a white dwarf, no hydrogen burning, no helium flash, no energy being created. What you see when you look at a white dwarf is not burning. It is the memory of burning, radiating outward at the speed of light from a body that is already dead in every thermodynamic sense that matters. It shines because it was once hot, and it is slowly, over incomprehensible timescales, becoming less hot. That is all. A white dwarf has no internal energy source.
It is held rigid against gravity, not by heat or pressure from ongoing fusion, but by a quantum mechanical effect called electron degeneracy pressure. The electrons inside the white dwarf, packed to a density that would be impossible under ordinary conditions, refuse to occupy the same quantum state. That refusal creates an outward pressure that exactly balances gravity's inward pull. The white dwarf is stable because quantum mechanics insists on it, not because it is doing anything to maintain itself. It is the most passive object in the universe, a ruin held together by a rule. The white dwarf will cool slowly. Over billions of years, its surface temperature will fall from 100,000 degrees to 50,000.
From 10,000 towards something approaching the temperature of the space around it, which is approximately 2.7 degrees above absolute zero, the remnant warmth of the Big Bang itself. This cooling process is so slow that no white dwarf in the observable universe has yet had time to cool to completion. The universe is only 13.8 billion years old. Even the oldest, most faded white dwarfs we have found are still faintly luminous. We have never seen this process finish. We are too early in the universe's life to observe its own dead stars going dark. At the end of this cooling process, the white dwarf will become what physicists call a black dwarf.
A cold, dark, inert remnant composed primarily of carbon and oxygen, compressed into a crystalline structure, something like a giant diamond. Not glowing, not radiating, not interacting with anything in any meaningful way, just present. A monument to something that once burned, now indistinguishable from the surrounding dark, except by its mass and its gravity. No black dwarfs exist yet. The universe has not waited long enough. The oldest white dwarfs have been cooling for approximately 10 to 12 billion years, and they remain faintly visible. We are living at a moment so early in cosmic time that the final stage of stellar death has never yet occurred. We know it will happen because the physics require it.
But we are, in a very real sense, witnessing only the middle of the universe's story. The end is still unimaginably far away. But here is something stranger still. Astronomers have found white dwarfs that are contaminated, not by anything exotic, by the ordinary elements of which rocky planets are made: silicon, iron, magnesium, calcium. These elements should not be present in a white dwarf's atmosphere. A white dwarf's gravity is so intense that heavy elements sink quickly, pulled down into the interior within thousands to millions of years. If silicon or iron is detectable in a white dwarf's atmosphere, it was deposited there recently in astronomical terms, meaning within the last few million years. Something fell in. What falls in is planetary debris. The shattered remnants of asteroids, moons, and rocky bodies that were disrupted by the white dwarf's tidal forces and gradually spiraled inward. The white dwarf's intense gravity tears apart anything that drifts too close, reduces it to dust, and that dust settles into the white dwarf's outer layers where spectroscopy can detect it. Astronomers read this contamination the way a forensic investigator reads trace evidence, as a chemical record of something that no longer exists in its original form. These are called polluted white dwarfs, and they are one of the most striking discoveries in modern astrophysics. They tell us not just that planetary systems are common around other stars, but what those planetary systems were made of.
A white dwarf that has absorbed a rocky body carries that body's chemistry in its atmosphere like a sealed envelope. By reading the spectra of these white dwarfs, astronomers have measured the compositions of extrasolar rocky bodies in a way that no other method permits. They are reading the ruins of other solar systems through the light of their dead stars. The sun's eventual white dwarf will almost certainly become polluted. The debris of the inner system, asteroid belt remnants, the shattered cores of worlds that could not escape the red giant phase, will drift inward over millions of years. Some of it will be torn apart by tidal forces. Some of it will fall directly onto the white dwarf's surface.
The chemical signatures of Earth, of Mars, of the entire inner solar system will eventually be written into the atmosphere of what the sun becomes. The sun will not forget the planets. It will carry them, dissolved inside its own dead body, for as long as the physics allow. There is something almost unbearably precise about this. All the geology of Earth, the iron core, the silicate mantle, the calcium in ancient bones, the carbon in every organism that ever lived, will eventually be read by some future observer as a faint spectral signal in the atmosphere of a white dwarf. Not as memory exactly, not as record-keeping in any intentional sense, but as the inevitable consequence of gravity and chemistry playing out to their conclusion.
The sun's white dwarf will be a document, and no one will read it.
The Earth is 4.6 billion years old. That number appears in textbooks and documentaries as a simple fact, almost casual in its presentation. But it is not simple. 4.6 billion years is longer than the human mind can genuinely process. If you compress the entirety of Earth's history into a single calendar year, first light of January would mark the planet's formation from the solar nebula. The first self-replicating chemistry would appear in February. The first true cells, prokaryotes, tiny and featureless by modern standards, would emerge sometime in March. And then almost nothing visible would happen for the rest of the spring and summer and into the fall. Complex multicellular life would not arrive until mid-November.
The Cambrian explosion, the relatively sudden diversification of animal body plans, would begin on November 17th. Dinosaurs would appear on December 14th. The asteroid that killed them would strike on December 26th. And human beings, all of recorded civilization, every monument, every war, every language, every idea that has ever been written down or spoken aloud or argued over, would occupy the final 11 seconds of December 31st. That is the frame through which you have to understand what is coming. Not as a warning, as a proportion. Complex animal life has existed on Earth for roughly 540 million years.
In that time, it has survived 5 mass extinction events, at least 1 global glaciation, and countless smaller catastrophes that we have only partially mapped. Life is resilient in ways that are genuinely difficult to overstate. But it is not eternal, and the window during which complex life is possible on Earth is not open indefinitely. It was never going to be. The mechanism of closure is not a single event. It is a gradient. Within 1 billion years, an interval that sounds long but represents only about twice the current length of complex life on Earth. The sun's increasing luminosity will drive a process called the moist greenhouse effect. As the sun brightens, more water evaporates from the oceans.
More water vapor in the atmosphere creates a stronger greenhouse effect, which drives more evaporation, which creates more vapor. The feedback is self-reinforcing. The oceans will not boil away overnight, but they will go. And as water vapor rises into the upper atmosphere, Ultraviolet radiation from the sun will break the water molecules apart, releasing hydrogen into space. Earth will lose its water permanently, not to a catastrophe, to a slow, unstoppable brightening. Without liquid water, the carbon cycle collapses. The carbon cycle is the geological process by which carbon dioxide is pulled from the atmosphere, through weathering, through the ocean, through the slow drift of tectonic plates, and returned via volcanism. It has regulated Earth's temperature for billions of years, acting as a thermostat that has kept the planet in the narrow band where life is possible. Without liquid water, the weathering step stops. Carbon dioxide accumulates. The greenhouse effect intensifies. The surface temperature rises past any threshold that complex biology can endure. 1 billion years. That is the window for complex surface life. It sounds vast, but measured against the sun's total lifespan, it represents less than 10% of what remains. And measured against what we have already burned through, the 4.6 billion years it took to produce us, it is a fraction of what has already passed. We are not early in the story. We are somewhere in the final quarter. Now consider what we have done in the time we have had. Modern humans have existed for roughly 300,000 years. Agriculture is approximately 12,000 years old. Writing is approximately 5,000 years old. The ability to transmit information across time and space without physical contact. Printing, radio, satellite, digital networks is a few hundred years old at most. The Industrial Revolution, the period in which humans began meaningfully altering the chemistry of the atmosphere, is approximately 250 years old.
The entire period during which humans have had the tools to contemplate their own cosmic situation, to ask where we came from, to map where we are going, is a rounding error on a rounding error on a rounding error. And in that rounding error, we have discovered the age of the universe. We have mapped the large-scale structure of space-time. We have detected gravitational waves from the collision of black holes 1 billion light-years away. We have identified thousands of planets around other stars and begun to characterize their atmospheres. We have developed the mathematics to predict the death of our own sun with meaningful precision. We have begun, tentatively, to think seriously about how to leave this planet. That is not a small thing.
It may be the most significant thing that has ever happened on this world. A species developing the capacity to understand its own cosmic mortality and to potentially act on that understanding may be rare. Genuinely rare, in the sense that the conditions required to produce it are unusual and the time window in which it is possible is finite. We do not know how rare. We cannot know how many other worlds have reached this moment and what happened next. We only know it has happened here. The case for leaving Earth is not primarily that Earth faces immediate danger. On any human timescale, it does not.
The case is that the window is not infinite, and windows have a way of closing faster than anticipated when the things keeping them open are complex and fragile. Civilization is complex and fragile. It always has been. The history of human development is not a smooth upward curve. It is a record punctuated by collapses of cities, of empires, of knowledge systems, of technological capacity. Writing was invented and then lost. Mathematical knowledge was developed and then forgotten for centuries. Agricultural civilizations, capable of building monuments, collapsed under climate shifts and social pressures, and the knowledge they held went with them. We tend to think of progress as durable because we have been in an unusually stable period for a few hundred years. It is not always durable.
A civilization sophisticated enough to spread beyond a single planet requires sustained effort across thousands of generations. It requires stable institutions, stable communication, stable energy, stable cooperation. None of these things are guaranteed. They have to be maintained. And maintaining them across geological timescales is an entirely different challenge from maintaining them across human ones. The question is not whether the sun will eventually make Earth uninhabitable. The physics are settled on that point. The question is whether anything that began here, any chain of complexity, any thread of organized information, any form of what we might loosely call life or mind or civilization, will still be present when the window closes.
Whether it will have made use of the time available to find a way to continue elsewhere, or whether it will have spent that time in other ways and run out of opportunity. Time is not on our side in the way we sometimes imagine. The universe is old, and it will get much older. But the period in which beings like us can exist, on a planet like this, in a stable orbit around a main sequence star, with liquid water and a breathable atmosphere and the slow accumulation of biological complexity that eventually produces something capable of asking questions about all of this, is not the universe's timeline. It is a narrow band within it, a flickering interval between formation and sterilization.
We inhabit that interval without having asked for it, and it will not last. The real enemy is not the sun. The sun is doing nothing malicious. The real enemy is the assumption that there will always be more time, that the window is so wide that urgency is optional, that we can defer the difficult questions about where we are going, about how we intend to use what we have been given, and return to them later when they feel more pressing. They may not feel more pressing until it is too late for the answer to matter. We are not at the end of that shift. We are nowhere near it on any timescale that touches human experience.
But knowing where the end is, knowing the shape of the entire arc from formation to extinction, changes what it means to exist inside the middle of it. It changes what registers as important. It changes the relationship between the ordinary details of daily life and the vast, slow machinery operating beneath them. It does not make every moment feel precious in a greeting card sense. It makes every moment feel specifically temporary. Temporary in a way that is not vague or emotional, but geometrically precise. We are here because a very specific set of conditions aligned for long enough to produce us. Those conditions will not hold forever. They will not hold for a time that is infinite or even especially long in cosmic terms.
The alignment is real and it is temporary, and both of those things are true at once. Knowing that is not a reason for despair. It may be the clearest possible reason for direction. Not urgency in the anxious sense. Direction in the sense of orientation, of knowing which way is forward and choosing deliberately to move that way.
Tomorrow morning, if the sky is clear, the sun will rise. The light that reaches your eyes
will have spent approximately 8 minutes traveling across the 93 million miles between you and the Sun. Before that, long before that, it spent somewhere between 100,000 and 1,000,000 years working its way outward from the solar core. It was produced deep inside the Sun by a fusion reaction, by 2 protons colliding and merging and releasing a photon in the process. That photon did not travel directly outward. It was absorbed almost immediately by the dense plasma surrounding it and re-emitted in a random direction, then absorbed again.
Bounced and scattered countless times, migrating outward through a solar interior so dense that light itself has to fight its way through. Eventually, it reached the surface. Then it crossed 93 million miles of vacuum in 8 minutes. Then it reached your face. The photon that touches your skin in the morning was born in a nuclear furnace long before your civilization existed. It traveled for tens of thousands of years through the body of the Sun, and then for 8 minutes through empty space, and then it arrived. This happens every day. This has been happening for 4.6 billion years. You do not think about it when you watch the sunrise. Neither does anyone else. That is not a failure.
It is simply what it means to live inside a moment, rather than outside it. The Sun does not know what it is doing to the planets around it. It does not intend anything. It is not cruel, and it is not generous. It is a ball of plasma, 400,000 times the mass of Earth, fusing hydrogen into helium at its core at a rate of 620 million tons per second, converting a small fraction of that mass, approximately 0.7%, into energy and radiating it in all directions. It has been doing this for 4.6 billion years.
It will keep doing it, in forms that will change as its fuel shifts, and its size grows, and its nature transforms, for approximately 5 billion years more. It will not stop being the Sun when it swells into a red giant. The red giant is what a sun-sized star becomes. It is the Sun's future, not its end. And it will not stop being the Sun when it expels its outer layers into a glowing, expanding shell of ionized gas, because that shell is made of the Sun. Everything the Sun will become is already inside it, waiting in the mathematics of stellar evolution. The white dwarf is the Sun's inheritance from its own physics, not a punishment, not a failure, a completion.
There is something steadying in that, if you can hold it at the right distance. We tend to think of the Sun as permanent, as given, as the fixed background against which the drama of life on Earth plays out. And within the span of any human life, it is. The Sun has been effectively the same star, within a fraction of a % of its current luminosity and size, for the entirety of recorded human history. It will remain effectively the same star for the entirety of human history as we can currently conceive it. The changes are happening. They have always been happening. The Sun has grown about 30% brighter since it first ignited, and it will grow brighter still.
But those changes happen on timescales so immense that permanence is not a delusion for any being whose life is measured in years or decades. It is a reasonable approximation. What we know that our ancestors did not is the shape of the whole arc. Not just the stable middle section we inhabit, but the brightening that will end complex life in 1 billion years, the expansion that will consume the inner planets in 5 billion, the nebula that will form and disperse in 10,000 years, and the white dwarf that will cool in silence for 1 trillion years after that. We know how this particular story ends, and that knowledge changes something about how we stand inside it. It does not make the sunrise less beautiful.
If anything, it does the opposite. The light on the horizon is not diminished by the knowledge that the source of it is a middle-aged star in the slow process of exhausting its hydrogen fuel. The warmth on your skin is not less real because the physics that produce it will eventually produce something else. What is real is real. What is present is present. The actual experience of morning light arriving after a night of darkness is not a lesser thing because its source is understood. Understanding does not reduce wonder. It changes its shape. It gives it depth. And what is here, right now, is improbable, almost aggressively so.
A star formed at exactly the right time in the universe's history. Late enough that previous generations of stars had already produced the heavy elements needed to build rocky planets, but early enough that the universe's accelerating expansion had not yet thinned out the cosmic structure too much for new star formation. A planet settled into exactly the right orbit, close enough for liquid water, and far enough to avoid the runaway greenhouse effect that claimed Venus. That planet developed a magnetic field strong enough to deflect the solar wind and protect its developing atmosphere. It accumulated water, delivered by asteroids and comets over hundreds of millions of years.
It developed chemistry complex enough to replicate itself, and then complex enough to store information, and then complex enough to build systems for modeling the external world. That chemistry evolved into cells, cells into organisms, organisms into nervous systems, nervous systems into minds capable of modeling not just the immediate environment, but the entire physical universe, including the star that made them possible. All of that happened in the available window. All of it accumulated during the stable middle period of a main sequence star's life, in the gap between the sun's formation and its eventual transformation. We exist inside that window. We are, in the most literal possible sense, the thing the window made possible.
And someday, not soon, not within anything that resembles a human scale of concern, the window will close. The sun will swell. The oceans will lift into vapor. The rocks will glow. The atmosphere will be stripped away or burned off. The surface of Earth will become a place that nothing we would recognize as life could occupy. And then, billions of years after that, the sun will eject its outer layers in a slow expanding cloud, and that cloud will drift outward, glowing faintly, cooling over 10,000 years into wisps of ionized gas that disperse into the interstellar medium.
And at the center of what was the sun, a dense white remnant will remain, cooling, silent, orbited by whatever survived the outer system, carrying in its contaminated atmosphere the chemical signatures of the worlds that once circled a living star. And somewhere in the vast dark beyond that system, out among the other stars, in other solar systems, on other worlds we do not yet know, there may be something that carries forward what began here. A chain of information, a pattern of organized complexity, a form of life, or mind, or civilization descended from the one that first looked up from this planet and began to wonder about the nature of things. Or there may not be. The universe does not guarantee continuity.
It provides windows, not conclusions. What happens inside the window is not written in the physics. The physics sets the boundaries, the timeline, the temperature ranges, the available energy. But the content of what unfolds inside those boundaries is not determined by the sun or the orbit or the composition of the atmosphere. We did not earn this window. It was given to us by processes indifferent to our existence, accumulating over spans of time that no individual can fully grasp. But we are the ones who can see it. We are the part of this system that became conscious of the system.
We worked out the age of the sun, and the timeline of its death, and the fate of the planets, and the slow cooling of the white dwarf. And what that means, what obligation or opportunity or simple awe that carries, is not a question the physics can answer. Tomorrow the sun will rise. The light that touches the horizon will be 8 minutes old, born from a fusion reaction deep inside a star that is 4.5 billion years through its 10 billion year life. The sky will go from black to gray to the particular shade of pale blue that means another morning has arrived. Someone will see it. Someone always sees it.
And one day, far beyond any reckoning that matters to anyone alive, beyond any civilization we can currently conceive of, the conditions that make a morning possible on this world will no longer exist. The sun will have changed too much. The atmosphere will be gone. The oceans will be gone. The surface will be something that has no word in any language we currently speak. But right now, in this moment, the sun is still doing what it has always done, rising in the east because the earth is still turning, crossing the sky because the orbit is still intact, sending light that started its journey in the core 100,000 years ago and arrived today, precisely on time, without knowing what it was arriving for.
The sun will rise until it doesn't.